your graphics is up.
Do you know where it should be?
Social distancing in here.
No, don't mind.
We're worried that it might be open again after first lockdown.
Let me just get some levels set for microphones, just to check that they're good level for you. So first of all, handheld. 1, 2, 3, 4, 5, 5, 4, 3, 2, and 1. 1, 2, 3, 4, 5, 5, 4, 3, 2, and 1. Welcome to Bletchley Park. The journey to a more secure future, the history of computers. I am your sound engineer for the day. 1, 2, 3, 4, 5, 5, 4, 3, 2, and 1. I will be setting basic levels, but if you guys can monitor them throughout the event, just to give me a nod up or down, that would be great. Because people will be speaking louder and softer, as we will find out. 1, 2, 3, 4, 5, 5, 4, 3, 2, and 1. Cool. And just do one for the lapel. I'm hoping not to use the lapel that much. I'm hoping it's going to be more for, they're going to use the lectern mic and the handheld, because if there's questions as well, I need to make sure that the microphone goes to people asking questions. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, a basic level. I'm going to give you about minus 40 dB for everything. So I'm going to come out just tickling the dB meter. And yeah, cool.
Yeah. would you be able to do me a scan of that? That would be great, because in the final piece we can muck about with that, digitally and push into bits. And yes, so it's Chris at suitedandbooted.org.
4, 5. 5, 4, 3, 2, 1. Microphone test. 1, 2, 3, 4, 5. 5, 4, 3, 2, and 1.
Mobile phones,
Yeah.
silent or off.
Yeah, silent, yeah.
Okay. Welcome, everybody. Thank you for braving Storm Franklin today to get here, and to everybody online as well. This is the first of the Digital Security by Design roadshows here at Bletchley Park. I'm Nitin Dahad, Editor-in-Chief of Embedded.com, which is a magazine for the embedded systems design industry, and also a correspondent with EE Times and EE Times Europe. So in this first of the four roadshows, we're going to be looking at the journey to a more secure future by looking at the history of computers. Before I go into anything, just housekeeping. We don't expect any fire alarms, so if there is a fire alarm sound, go out through the exit which you just came in through. And also, mobile phones to silent, please. We've got both of here as well as online, so it'd be good to have that. So yes, in this talk today, we're going to be looking at the journey to a more secure future by looking at the history of computers. We need to do that, look at the history to go to where we need to go to next. But before that, just a bit about Digital Security by Design, DSBD. It's an initiative to make computer systems architecture more secure by design. That is to radically update the foundation of what might be considered insecure digital computing infrastructure that we have today. And the idea is to create a more secure hardware and software ecosystem built on new security capabilities, and the initiative hopes that the technologies developed will underpin future digital products and services. And details are all on the website and in the blog. dsbd.tech. The four roadshow events will take us through the journey to delivering this by setting the context, as I said, through the history of computers. And then in the next one, exploring new technologies in cybersecurity. The third one will look at strengthening the foundations of computer architecture. And the last one will be on the future of trusted computers. So it's all going through a journey, a story, and how we're going to get there. In this first event, we explore the history of computers, and what better way to do that here with Sir Dermot Turing and at the National Museum of Computing at Bletchley Park. After Dermot sets the scene, we'll have Dr. Andrew Herbert OBE. He'll talk about the history of computer performance. And then, via video, we'll hear from Professor Genevieve Lively about looking back to look forward and the art of futures thinking. And the final talk will be by Andrew Elliott, who will talk about the ubiquity of computers in the digital world. In case you're wondering, we have Chris here, the scribe, on my right, and he'll be visualizing the event. So don't be distracted, but yeah, I'm sure you'll enjoy all his visualizations of what we talk about. And then also, this is being sort of active on social media. We have colleagues from DSBD tweeting, so feel free if you want to tweet, LinkedIn, Facebook, whatever you use. I don't use TikTok, but I guess we could. Well, let's get started. Let's get started with Sir Dermot Turing, acclaimed author of Prof, a biography of his famous uncle, the story of computing, and most recently X, Y, and Z, or if you're in the States online, Z. The real story of how Enigma was broken. He's also a regular speaker at historical and other events. Dermot, over to you.
Thank you very much. Good morning, everybody. Welcome to the National Museum of Computing. And those of you who heard the TikTok plug, I'm going to be very disappointing to you all because I'm not planning to sing or dance. Any singing or dancing that you witness is entirely accidental and not intended as part of the presentation, which is supposed to be something very serious on computing, Alan Turing, and the origins. Okay, let me just do a little bit on linguistics here. I find this quite intriguing. Here we are, we're at the National Museum of Computing. What you see here in the museum is largely a bunch of computers, and you have to sort of tease out the software side of things as you go around the museum. In the very earliest days, my sense is that the distinction between the hardware and software sides was much less well defined, much less separated than perhaps it is these days. And I suspect that as this series of presentations goes through, one might see that the two are not perhaps as disconnected from each other as you might think. So I just find this quite intriguing that we've got the history of computers. We're here in the Museum of Computing, and I'm going to talk about Alan Turing and the origins of computing. And we're going to begin with this, which is, we'll get there eventually, Alan Turing's famous paper on computable numbers. Now, fantasy and reality. Those of you who have studied computer science may have been forced to digest Alan Turing's paper on computable numbers because it is said to be the source of, if you like, the blueprint of the digital computer. It's a bit of a sort of a fantasy idea, really, because Alan Turing wasn't thinking about computers at all when he wrote this paper. What he was trying to do was to create a new part of number theory, which was to define things. I mean, we all know about prime numbers, we know about rational numbers, and he was trying to define a new class of numbers, which are computable numbers, and to explain what he meant, he tried to get you to visualize this idea of a sort of a funny kind of a machine with an infinite tape, and the machine could essentially be instructed or programmed to do different things. And this whole idea of programming, Alan Turing invented the computer program. Well, but Ada Lovelace already did that. Anyway, so it all gets a little bit sort of confused. And then there's this question about, well, what was a Turing machine actually going to look like? And so you get these fantastical ideas come out of graphic designers' heads about what a Turing machine might actually have looked like. He never actually conceived that it would have a three-dimensional reality, even though people have actually, this one is from the Heinz-Nixdorf Museum in Germany, so and incidentally put together by a German codebreaker whose job it was to test out the security of Enigma from the German side. So very interesting guy called Gisbert Hasenjäger. Spent some of his time in the post-war years actually creating a Turing machine in 3D hardware. which was never part of Alan Turing's concept. So, the origins of computing and Alan Turing, do they begin with computable numbers? Possibly, I say. What was Alan Turing himself doing when it came to hardware computers? So, when he stopped working on this kind of theoretical thing, he was still quite interested in something called the Riemann Zeta function. And for those of you who are mathematically inclined, this is the Zeta function up there. And Riemann's theory was that when the real part of S in zeta of S is a half, then zeta of S is 0. And this is very exciting to mathematicians, but these sums are incredibly hard to do. So what you do is you approximate to this thing, which is this trigonometric formula up there, and then that becomes within computable reach. Alan Turing's vision for how you would solve these equations, or basically do numerical analysis on these things, was to use a piece of kit basically designed not dissimilarly from a tide predicting machine that had been invented by Lord Kelvin at the turn of the previous century, which was at that time available to view in Liverpool. It isn't anymore. It's been whisked off to some museum in France, and I don't know that it's actually on display anymore. But you can see there's all these sort of pulleys and things which will actually behave like a cost function and interact with each other. And so basically he got one of his engineering colleagues at Cambridge University to draw up this rather splendid piece of blueprint for a machine that was going to operate in a similar way to the time predictor, but this time be able to calculate the Riemann zeta function. They started building this thing, and there were brass cogwheels all over Alan Turing's floor in his rooms at King's College, Cambridge. The war broke out before they started to assemble it, so it never actually got made, this thing, and I don't know what happened to the brass cogwheels. But what you can see instantly from this thing is that this is not what these days we would recognize to be a computer. I think that's possibly a piece of semantics, but this is definitely an analog machine. It's not digital. The contrast between this piece of kit and the Turing machine, which has this sort of programmable concept, it could not be more extreme. I mean, I don't think that he had any idea in his mind that the future might be formed of a sort of fusion between these two concepts of a programmable machine and a calculating machine, which is basically what this is. So that takes us to roughly 1939, where you can see things are really a bit of a muddle. I think 1939 is very interesting indeed, because 1939, here at Bletchley, we get into the world of machinery to help with code breaking objective. What you've got on the top left there is the bomber machine invented by the Polish code breakers in the pre-war years, and the bomber machine's job was to test digitally for the correct setting on an Enigma machine. I'm not going to do the whole spiel about Enigma machines. I hope those of you who haven't seen it before will spend some part of today going and seeing a bomb demo in this very museum, where they will take you through how the Enigma machine works if you don't already know, and if you don't, you should be ashamed of yourselves. But also, much more importantly, and there's much less shame associated with this, which is how you use a machine to find the settings on the Enigma machine, given that there's 150 million different ways of setting up the Enigma machine every day. So that was the test. So the Poles developed this digital piece of kit which would test for the correct setting. And they basically donated their technology and their ideas to the nucleus of code breakers working on the Enigma problem at Bletchley Park 6 weeks before World War II broke out. And that was what enabled Alan Turing and his colleagues to design the bomb machine that you can see over there. It's a much more souped up, much cleverer version of the Polish bomber. And you can see a blueprint from the Bletchley Park collection of drawings designed to help with the design of the bomb machine. So I think this is quite interesting. This is digital technology. It's not programmable digital technology. On the other hand, at Bletchley Park, and this is one of the unsung heroes of the story of computing, the biggest machine facility here at Bletchley Park was punched card processing technology. The visitor centre of the Bletchley Park Trust in Block C down there was full of punched card machines which were being put to work on all sorts of sorting and analytical problems. The punch card machines were supplied by the same company that designed and built the bomb machine. That's the British Tabulating Machine Company. The British Tabulating Machine Company had the franchise from IBM to produce punch card technology in the UK. And there's lots of stories around that. But what you can see here is that punch card technology needs to be, I think, put on a same par with the bomb machine. The bomb machine is very clever, but it's single purpose. The punch card technology is multi-purpose. It's programmable stuff. And I think that people think of programming as something that sort of started after World War II. It's not true. People have been programming punch card machines to do all sorts of different jobs before the war. And that technology was here on this site. Nobody talks about it. I don't really understand why. It's because we're sort of so wowed by the Enigma problem, we forget that the punch cards were actually used to help solve Enigma problems as well. But we have to whitewash that out of the story because we're so obsessed with the idea that the bomb is sitting there in the historical canon of how Bletchley Park, Enigma, World War II, invention of computing, and so forth. I'd just like to correct that slightly. I think we've got lots of sort of different factors coming together at Bletchley Park, people seeing all these different computing machines and different techniques of computing and seeing how you could perhaps meld the different types of versatility and get better. So I just want to shift the focus over to the other side of the Atlantic for a moment, because I think one of the forces at work comes from over there. When the Germans introduced a four-rotor Enigma machine for use by U-boats, this became a serious threat in the Battle of the Atlantic, and I expect you all know that for several months the Bletchley Park codebreakers were locked out of being able to read German naval, and in particular U-boat, Enigma messages, which meant that the convoy sinkings skyrocketed and the ability to track down and kill U-boats correspondingly plummeted. The Americans started working on the four-rotor Enigma machine problem by building their own four-rotor version of a bomb, which interestingly had electronic components in it. Because the machine ran so fast, the problem was that the rotors overran the setting that they had found, which was the plausible setting for the four Enigma rotors. When the rotor's spinning so fast, the fast one overruns the stop position. So how would they solve that problem that it's stopped, but the momentum has just carried on beyond the point that you're actually trying to identify? So what they did was they put this component on the top of the four-rotor bomb machine, which was basically an electronic memory to be able to remember the correct stop position, even though the rotors had carried on spinning. So they're using electronic components, but they're not really using them for programming, which is, I mean, it's interesting, but it's perhaps, not a sort of a breakthrough in terms of digital computing. What I think is more interesting, and again, this, for whatever reason, doesn't seem to have captured the imagination of those who write papers about this stuff, is the American Army bomb. So the US Army were working on bomb machinery as well. Having visited Bletchley Park and seen the Turing-Welshman bomb that you can see here, they took the idea away and said, yes, but we are held back here by the fact that we've got rotating mechanical parts. We could actually recreate the functionality of these rotating mechanical parts in switching technology using basically relays from telephone switchboards. And so the US Army joined forces with Bell Labs, which was basically the Bell Telephone Company, the equivalent of the GPO in the UK, had this huge technology research facility, and they built essentially a fully digital, no rotating parts version of the bomb machine, which you can see a couple of photographs of. I mean, the trouble with doing it this way is that you need vast amounts of kit to be able to replicate using switching technology what you get from a single rotor on the bomb machine. You need sort of a vast rack of relays and switches. But I think this is very interesting because what they were doing with the US Army bomb is recognizing that switching not only could replicate the function of the moving parts on the bomb, but it could also be reprogrammed, because all you needed to do was add some peripherals to it, and then it could solve other problems. So to turn a US Army bomb into a four-rotor bomb was no problem. It just needed a bit more kit. To turn a US Army bomb into solving particular Enigma problems, like, for example, where there was some garble in the way that the settings had been communicated, then they could use this, they could basically stick add-on pieces of kit. It was just a matter of somebody sitting down and actually working out what the circuitry was going to be. That's what, in those days, we might have called programming. And I think this is very interesting, because what we've got here is the bomb story exploding into a variety of different species of not just computers, but also computing. Alan Turing was aware of all this. He consulted with Joe Desch, the designer of this thing. He was allowed in very reluctantly from the American perspective to see this thing happening, and these things sparked his own views about what he was going to be doing in the post-war years. Now, famously, we know that Alan Turing came up with his design for the automatic computing engine, the Britain's answer to digital computing. Apparently, this makes me laugh, the committee of civil servants who were tasked with the job of pushing the UK computer project along in 1945 debated long and hard about whether they should have more than one computing machine. After all, there are only so many ballistic trajectories that you need to calculate in any given year, which implies that one computer should be sufficient for all of Britain's computing needs. They decided, though, that they should probably have two in case the first one broke down. Great. So Alan Turing's design for that was done by the end of 1945. It didn't take him very long, but he was, once again, as with the Polish stimulus on the bomb machine, he was stimulated by a paper by John von Neumann, which was the first draft report on the EDVAC, which he had been able to, there weren't very many copies of it, but he'd been able to see the British copy of it in probably just after the war in Europe had ended, probably June, July 1945. And I think that this showed him how he could take his own ideas about programmability, or rather what in those days they were called instruction tables for machines. Von Neumann himself, influenced by Alan Turing's paper on computable numbers, von Neumann takes it into what we all know these days as the von Neumann architecture, as described in the first draft report on the EDVAC. Alan Turing then takes it to another dimension, which is to say, okay, taking all these things, this is how I would design this machine, this is how much it's going to cost, this is how you're going to build it. It's just a little bit of a problem with this is how you're going to build it, because they didn't actually get around to building it for another 13 years, by which time Alan Turing was dead. The ACE was a piece of basically obsolete kit. I mean, it worked great, but it was huge, and the world had moved on by that stage. Okay, so let's just pull all this together, because because I'm in danger of sort of trespassing onto the territory that Andrew Herbert's going to talk about in a minute. But before World War II, we have essentially obstinately analog computing machines such as the Hartree differential analyzer, and we have digital data processing machines using punch card technology, and it seemed to be very difficult to hybridize those two things. What becomes very interesting is that the key technological development that the code breakers latched on to begin with all came out of the digital world, all the stuff designed and built by BTM, most notably, of course, the Turing-Welshman bomb, but not ignoring the dependency on punched cards for code-breaking purposes. Just to give you a sense of the scale of that thing, 7 tons of punched cards a week being got through, notwithstanding the paper shortages during World War II. That's an awful lot of kit. That's an entire truckload of punch cards being got through every week at Bletchley Park. Okay, so Turing-Welshman bomb, obviously that spins off into the Joe Desch bomb, which is just basically a bigger Four-Rotor version with electronic components. But I think more interestingly, spinning off into the US Army bomb with its versatility and its programmability and its abandonment of the idea of specially tailored moving parts. So you could use the US Army bomb for anything as long as you were willing to reprogram it, which basically meant reassembling the units to fit together in novel ways. While we are talking about technology, computing technology during World War II, it would be remiss of me not to mention Colossus, even though its links to Alan Turing are very tenuous. I should probably, for the record, say that Colossus has nothing to do with Enigma code breaking. Still, people are a bit confused about that. The Colossus rebuild here at the National Museum of Computing will set you right on everything that you should possibly want to know about what Colossus was for. But I think that what you can do with Colossus in this particular context is recognize that the machine groups here at Bletchley Park, once they realized what the capabilities were of electronic technology and very new emergent technology in the early 1940s, they could meld that with what they had learned from things like the bomb project and the programmability that they were seeing coming out of things like the US Army bomb. Now, I think that the Colossus is really a huge technological development, and it's got this tiny element of programmability to it, so that the mathematicians at Bletchley Park were very excited to be able to play with Colossus in its few moments of downtime, because they thought that they could program it to do long multiplication. Just be such fun. Okay, and I think that when you then go forward to the post-war computing machines, you'll find that all the ideas that I've just been talking about come together in different ways with different people and different influences on things. I picked out the EDSAC just as an example because that's here at the museum, and you can go and have a look at it later. The EDSAC team is not particularly connected with the work done at Bletchley Park, and the EDSAC team did not, of course it didn't contain Alan Turing, because Maurice Wilkes, who was the driving force behind the EDSAC, Maurice Wilkes and Alan Turing really, shall we say, didn't get on particularly well together. So they exact contemporaries at Cambridge. They both got, they were both B-star wranglers, which is the top grade of mathematics graduates at Cambridge, and they couldn't stand each other. It's just, it's one of the fun bits of the story of computing. But anyway, I hope that sets the scene for you about Bletchley Park and its relationship to the origins of computing and the role that Alan Turing may or may not have had in some of this. He's definitely there. I'm not whitewashing him out of it. He's not the only player. Anyway, thank you for listening. I hope you enjoy the rest of your day.
Thank you, Alan. That was really fascinating. You know, what I took out of that is, you know, the punch card machine was overlooked. The US Army, you know, introducing switching and programmability. And the bomb story, exploding into a variety of species of computers and computing. And obviously, you know, von Neumann and Turing, you know, the inspiration and influence they had on each other. So thank you very much for all of that. Next, we're going to hear from Andrew Herbert OBE from the National Museum of Computing here at Bletchley. And he'll talk about the history of computer performance. Obviously, a perspective that he's got here from the National Museum of Computing. Andrew spent his working life in computing, initially as an academic at Cambridge University Computer Laboratory under Sir Maurice Wilks, often regarded as one of the fathers of computing. He then worked in various entrepreneurial computing companies, developing key technologies and gaining insights of the rapidly growing digitization of the modern world. His last full-time role was as head of Microsoft's research laboratories across Europe, the Middle East, and Africa. Andrew, welcome you to the stage.
So Dermot conveniently put up my first slide for me. So I'm going to give you a perspective of the history of computer performance. I was set this as a question by the organisers of the event, a history of performance, that kind of, what did that mean? What I've turned it into is a quick run through the history of computer architecture, which is really where performance has come from, and try to link it to some of the machines in the museum that you can see here as icons of some of the major developments. And as I did that, I kind of made two discoveries, and it might just be because of the way I did the research behind the talk. Everything was kind of settled by 1975, and the Brits were behind most of it, which is really rather fun, as we're here talking about digital security by design, obviously based on the ARM processor. And I have, and the Cherry architecture. And I have an affection for the Cherry architecture. I did my PhD at Cambridge in 75 to 78, while Maurice is still running the department. And that was on what we called protection in those days, which was kind of digital security by design, but we didn't have words like digital and design at that point. And I micro-programmed the capability architecture. One of the amusing aspects when the Cherry project first started, academic days, of various students saying, where can we find your thesis online? Well, my thesis was written before there was an internet, so it was hand-typed by my then girlfriend, who became my wife, and it's in the university library if you want to read a copy. We had one big trouble with trying to do digital security by design in 1975. We didn't have enough transistors, and that's what's different in the modern age. So let me take you back into history. I think most of the gains we've seen in computer performance have come from new concepts in computing architecture, and alongside that, the increasing miniaturization that electronics has given us, like moving from relays to valves to transistors to microelectronics. Those two things have gone hand in hand. The miniaturization has given us the transistors to spend on putting new things into computer architecture that give us better performance for programmers. As I go through the talk, we'll keep coming back to the fact that computer memory has been the Achilles heel. It's been that all the way through the von Neumann approach to designing a computer architecture. And indeed, because of that, we're starting to see, in many areas, a move away from that founding vision. Another aspect of the development of computer architecture that fits with the theme of today is, as computers have got bigger and faster, those of us who come more from the software side of the story have had the conceit to write larger programs and then been surprised that they go wrong and have bugs, and that's thereby created the cybersecurity challenges. And so there's an obvious question to be asked, which I won't address in this talk. He says fishing for an invitation to give another one, is can computer architecture help here? And that's really what the rest of the day is about. So you're now going to get a computer architecture course that should take about a term in Cambridge, compressed into about 18 minutes, but we'll see how we do. So I'm going to pick up where Dermot left off with EDSAC, which folks from Cambridge, of which I'm one, claim is the world's first practical electronic digital stored program computer. You notice lots of adjectives there. Anyone who's claiming first something about computing then chooses a set of adjectives that carefully positions their machine in the right place. And really the only claim amongst all the early machines that EDSAC has was it was practical in the sense that other people than those who built it could use it, and it was used to solve real-world problems for those people. Other machines, earlier machines, have much been focused on understanding the concepts and the circuits and so forth. The other important word in there, again picking up from Dermot, is stored program. That you wanted to build a general purpose machine, you wanted to change what it could do to solve different problems. You didn't want to do that by rebuilding it, you just wanted to do it by changing the contents of what was in its memory. Which goes back to the Turing machine concept, that there was this tape which had a memory on it, and that some of that memory, as well as being data to be processed, could be instructions for this conceptual machine. And that's what von Neumann put together in his report with the von Neumann architecture, was a machine with a memory that could contain data and instructions on how to process that data and input-output devices, so it could take more data in, and it could send results back. And indeed, von Neumann's report was intended to lead to building an American machine called the EDVAC, which was indeed built. EDSAC was built by Wilkes and his team at Cambridge. Like Turing, he'd had early access to the von Neumann report. He went to a workshop at the Moore School at the University of Pennsylvania, where von Neumann and others talked about their proposals. And essentially, EDSAC is EDVAC built on the cheap as a small miniature version to try out the ideas. And that's why it was built 5 years ahead of EDVAC getting built. The most important architectural part of EDSAC was the store, which was, as in this picture here, long tubes full of mercury. The calculating part of the machine was indeed electronic, using valves, but you could not build a large memory out of valves. Valves at that time were quite large. They're about that tall and about that in diameter. If you've got 3,500 of them, as you have in EDSAC, you're already drinking 9 kilowatts of electricity just to do the calculations. It takes 5 valves to build a flip-flop to store 1 bit of memory. So if you want 1,000 words of 17-bit memory, as EDSAC has, that's 1 aircraft hangar and 1 nuclear power station, and they hadn't quite got nuclear power stations in 1947. So you had to do something else. And the idea of the Mercury delay line is you send acoustic pulses down through this tube of mercury. They travel at the speed of sound, whereas electronics is going at the speed of light. So you slow things down a bit, but you can store about 600 bits in 5 meters of mercury. And that's how the store worked. And if you have lots of tanks together, then you can start building up a memory. And the EDSAC machine, by the time it was complete, said had 1,024 words of what to the programmer was 17 bits. At the hardware level, there were actually 18 bits, but 1 bit wasn't usable by programmers. And the whole performance of the machine was essentially limited by the fact that if the data you wanted had just gone into the tube, you had to wait for it to travel along before you could take it out again and process it. And so EDSAC ran at a magnificent 650 instructions a second, but that was 1,500 times faster than a PhD student with a hand calculator that was the alternative technology. And arguably that performance jump from the PhD student with the hand calculator to an electronic machine, albeit with a slow memory, was probably the biggest single step function we've had in calculating speed. We've got very excited about Moore's law and performance doubling every 18 months or whatever, but we've never seen a 1,500 times performance jump. And so if you're an EDSAC programmer, you had this major cycle picture in your head all the time, that if you're really unlucky, the bit you wanted to read had just gone into the store and you had to wait for it to come round again. And that's where that's one area where Mr. Wilkes and Mr. Turing fell out, and I might talk about that in a moment. So all the early machines were based on a concept called serial computing. And the idea was that essentially you do arithmetic the same way, certainly my generation was taught it at primary schools. You work digit by digit. You do the units, then the tens, then the hundreds, then the thousands, except we're in binary, so it's the ones, twos, fours, and eights, and so forth. So inside the machine, you had a register, an accumulator, like a modern machine. As you were operating, the bits would come flying in from the right into an adder. The adder could add 2 binary digits and generate a carry. You delayed the carry, so you waited for the next 2 bits for the next position to come through, added the carry in, and you got your sum. And so when you visit EDSAC, although it's physically huge, all 2 tons of it, all 3,500 valves of it, actually the heart of the arithmetic unit knows how to just add 2 bits. But again, that's a lot of vowels. And so you've got a very slow calculating system. It's working digit by digit, and a very slow memory inside the machine. But in 1947, with that, you can build a machine that can add, subtract, multiply. EDSAC doesn't divide. You can do divides by calculation if you've got the others. And you can run useful programs that solve significant problems in things such as radio astronomy and biology. And so with the aid of your computer, 3 or 4 of your colleagues can get Nobel Prizes, which is one of the claims for EDSAC. And indeed, if you read the Nobel acceptance speeches of people like Martin Kendrew and Martin Ryle, they name EDSAC as if it was a scientific collaborator in the team, because without that computing power, they wouldn't have been able to do the science they wanted to do. So we started serially. The architecture of EDSAC is exactly von Neumann. You have a store to remember things from which you can fetch program and data. You have a control system. You have an arithmetic unit, which has one register, the accumulator, and you have input-output. That's exactly stolen, if you like, in conceptually from the von Neumann reports. And the physical implementation of the machine is really very straightforward. Because everything is serial, you've got the store, you've got the arithmetic unit, the bits are progressing around the machine, you open and shut various gates to let things shuffle out of the store, come into the arithmetic unit, which is how you can add a number to the accumulator, and when you've got the result, you open the gate here, and it can shuffle back into the storage unit. What's this strange thing called transfer units? Well, electrically, things go badly wrong if you have an input and output gate open simultaneously, so you delay things in the middle, you capture the results in the store, and then on the next cycle, you take them around into the input. So all the performance things on EDSAC are about sort of slowing everything down in the memory, doing the arithmetic serially, delaying the cycles around the machine. But it did its job. So we've talked about the von Neumann architecture. Actually, I want to go back one thing. The only other thing that needs to be talked about in the von Neumann architecture is you have the idea of sequence control. There's some sort of register. These days we call it a program counter that essentially tells you which instruction to execute next, and you have some sort of instruction in your order code that allows you, based on some condition, to go somewhere else in the program, and that's how you can take decisions. And so you fetch an instruction, you decode it, you read an operand. If you're, for example, adding something to the accumulator, you execute the instruction, and then you go to the next in the sequence. Turing had a different model. He looked at the von Neumann architecture and the way people were building machines, and was really concerned about this delay in the access time. And the fundamental question he asked was, can we lay out the program so that the next instruction or data we need is coming out the tube when we need it? And so starting to program given the design of the memory. And that's the architecture of the pilot ace. The instruction format is really quite different. I'm not going to go down into the great details, but essentially the machine was designed so that cycle by cycle you could choose where you were taking data from, what kind of operation was being applied, and where it went to. And if you're a cunning programmer with a lot of smarts, you could build a very, very efficient program, because essentially you are optimizing for the construction of the machine. And that meant that when his machine was built, the Pilot Ace, and there was a commercial spin-off by English Electric called the Juice Machine, they were the fastest computers in that time. They outpaced machines like EDSAC and its successors. And so they were able to solve some problems in the late 1940s, early 50s, which couldn't be tackled by the von Neumann machines. But they were a nightmare to program. You had to have an Alan Turing-type brain to program them, whereas the von Neumann machines were simpler to program. And the vision that Wilkes had was to try and democratize computing by making it easy to write software. And if that meant you had to do things in the hardware to make it easier to write software, so be it. You shouldn't expect programmers to really understand the hardware. The next big change came when we moved on to magnetic core memory to replace delay lines. This is a memory based on little coils of ferrite, which you can make spin not magnetically spin one way or the other, which gives you ones and zeros. With that, you can build a random access memory, because you can access any core in that framework by driving an X and a Y coordinate. And it's the same time, therefore, to access any location. You can put planes next to each other, so you can read in parallel, so you're not waiting bit by bit. You can work word by word. And the first machine we have in the museum here with a core memory is the Elliott 803. It's an interesting transitional machine. It has core memory. It's built using transistors. We've moved from valves to transistors. Although they're germanium transistors, we're not yet quite in the silicon world. The arithmetic is still serial, because those germanium transistors were expensive, even though they're smaller than valves. But we have a core memory so that we can read and write out of the memory in parallel. The next step in performance, as we've moved into this parallel world, is to start using inexpensive silicon transistors that become available in the late 50s, early 60s. And then as you go around the museum, you'll meet the Elliott 903. Our one dates from about 1967. I had the pleasure of learning to program on one of these as a schoolboy. And it's a machine that was typically used in small research laboratories, in a lot of process automation applications. There were military versions, there was an avionics version. About 1,000 of these were made in the late 60s, early 70s. It's a parallel machine. This is the internal architecture. All you have to take away from it is in all the boxes of registers, it says 1 to 18. It's an 18-bit machine. And when you do an add, it just adds 2 numbers in 1 clock cycle. Bang, done. So we've already got a speed up of at least, as it were, 18 times, because we're not doing it bit by bit. And because we've got more transistors, we've got a lot more internal structure than you see inside EDSAC. Interestingly, the company who built the Elliott's machines, Elliott's were based in Boreham Wood, quite near Cambridge, and there's a lot of Cambridge influence in the Elliott histories. So 18-bit wide data paths, a parallel adder inside the machine. The next idea that came along came from Manchester. If you're writing a program, you quite often want to work on things like vectors and arrays, if you're multiplying matrices, for example. If you want to do that on EDSAC, you essentially had to modify your program to march its way down through the data in the memory, because there wasn't any kind of register that pointed into the memory that you could use. So you wrote self-modifying code, which was clumsy, and it was wasteful of instructions. People in Manchester, which is kind of the other centre in the UK for early computer developments, invented an extra register, which they magically called B, because the first register was A for accumulator, and that concept was adapted in EDSAC. And with this second register, you can use that to point into the memory. you could increment the second register, and you can therefore start walking down data in the memory of the machine much more efficiently. So that came from Manchester. These days we call them index registers, and that's because IBM, as always, took someone else's idea, put their own name on it and claimed it for themselves. But actually index registers came from Manchester. A couple other things that came out in the early days. Another Cambridge idea. The challenge with EDSAC is every rack of circuits is unique. There's no interchangeability. So if any one rack breaks, you lose the whole machine, and you've got to fix that chassis before you get the machine back. When they built their successor machine, EDSAC 2, they went for a different approach, and it's the same approach is used in the 903. It's what's called bit slicing. So in the 903, there's a rack of cards, got myself in the middle here, which is where the processor is organized, and the card is there on the left. Each of these cards has one bit of every internal register, one bit of each of those data paths, and then you put 18 of them next together, and you've got your 18-bit parallel machine. And the nice thing from a maintenance point of view is it's easier to keep a few spare of those cards, and if one of them dies, you just put a spare in. So you start thinking not only of parallel architecture, but also a bit slice way of constructing it. And that's an idea that still exists today, building a processor out of modules of smaller bit width processors. Another idea which appears in the 903, which also started in Cambridge with the EDSAC 2, as we started to build more powerful machines, we started putting more in the instruction set, like the divide instruction came in. And particularly as machines got involved in data processing, there were thoughts about having instructions that would do sorting in memory of data and so forth. And that meant the electronics got more and more complicated. And indeed, there was much debate in the early days about what instruction sets should and shouldn't look like. The Cambridge solution to that was to have the core of the machine very, very simple, and then have a very fast memory which had inside it a microprogram that knew how to turn the instructions the programmers saw into the low-level operations inside the machine. This is some of the microprogram for the Elliott 903. You don't need to read the details, but you can see there's essentially a flow chart there. They're the little tiny steps of opening and shutting gates in that early picture of the architecture. I think this is the conditional functions. And this is the microprogram as it's physically realized. It's a lot of little diodes that give you ones and zeros in essentially a very fast memory, and some amplifiers to read them in and out. And that's the concept of microelectronics, of microprogramming. That was particularly helpful as instruction sets got more and more complex, which we call complex instruction set computers. And they were very dominant in the 60s and 70s, and arguably still with us in the Intel architecture, and explain some of its challenges. The other advantage of microprogramming is already by the 60s, and certainly in the 70s, the idea of having a range of different processors of different performance capabilities, but with the same programming interface has started to establish itself, so that software could be portable. And microprogramming was a nice way of solving that. On the smaller machines, you can microprogram the complex instructions rather than build them in electronics. Next machine I want to call out is the English Electric KDF-9. Sadly, we don't have one in the museum. I'd love to have one because I used one as an undergraduate, and for a while that was my girlfriend. We're in the early 1970s now. Not the one who wrote the thesis. There you go. Because I've moved different university. This machine was interesting that they looked at the next speed up. It had what was called an instruction buffer. So as it was running programs, it remembered the previous instructions in a fast memory. And there was a special jump instruction. And if you're a cunning programmer, you're kind of stepping back into the Pilot Ace world, you could use a special jump instruction that would take you back in that sequence, so you have a very, very fast loop running out the instruction buffer. And so it ran very, very fast with no overhead, no fetching from memory, because even core memory is still slow compared to electronics. And the KDF-9 was very much designed as a numerical machine for doing calculation. It came from English Electric. It was a successor in many ways to the Deuce, which was based on the Pilot Ace. So some of that thinking still fed through. So we had the instruction buffer. The question is, can you generalize that idea? And that is the next architectural kind of development. And I really have struggled to pin down where this came first. My brand loyalties make me want to say Cambridge, because there was one on the Cambridge Titan. It was called a slave store, and I'm told that's a politically incorrect way to describe a cache memory in this modern day and age. And the idea was you had a very small, fast associative memory between the central processor and the main memory. So when instructions were being fetched or data was being fetched, you put them in the cache, and one of the properties of most programs is they exhibit what's called locality. They're typically running around a loop, obeying the same instructions or working on the same data. So if you have a big enough cache, it fills up with the working program and the working data. And because it's a faster memory, more intimately connected with the CPU, you see the performance speed up. And that idea obviously is there in spades in modern computers with multi-level caches. There are some challenges. Obviously, you want to build your cache as big as possible. That wasn't so easy in the 60s and 70s. We didn't have the transistors. And at some point, if the data changes, you've got to put it back in the main memory. How and when do you do that? And if you get to multiprocessors, you then got caches competing for the data. There's some interesting design choices there. This is a cache memory out of the Cambridge Titan machine from about 1965. And if anyone can point me at references to cache memories earlier than that, I would be pleased. I think it was another Cambridge contribution. So the next development after that, we've speeded up the memory as fast as we can with cache memories, was pipelining. And the idea here was, can we, rather than doing one instruction after another, start to overlap them? And this essentially is doing instructions in parallel, keeping every bit of the processor busy. So, whoops. I thought there was supposed to be a build on this slide. We've lost it. Never mind. But if you look at the typical instruction, as I specified it earlier, you have a fetch of the instruction, you decode the instruction, you typically have a fetch of an operand, you have the execution, and then possibly the write back of a result. If you can overlap those steps, while I'm decoding the current instruction, can I be fetching the next one? Then essentially you're speeding up things as they go through the machine. Obviously there's some challenges there. If later instructions depend on the result of previous ones, you can't let one get past the other. What do? Well, if you detect that, you can just, as it were, stop the clock and spread everything out. If you're cunning, you can find ways to send the data forward faster. And if you're really cunning, you execute the instructions completely out of the order the programmer wrote them, but in a way that doesn't mess with the results that are being produced. And the particular challenge in all of that is dealing with jump instructions, because they change the flow of control. But all that stuff was kind of sorted out, again, in the late 60s. The Americans were certainly doing this with machines called Elliott and the IBM Stretch computer, but also Manchester University and Franti with the Atlas machine. I think the Americans were there first, but certainly the Atlas had pipelining, and that was there in about 62, 63. That takes us to the debate about complex versus reduced instructions. The complex instruction sets made sense when we wrote programs in assembly code, because essentially it took fewer instructions to do something complicated, so there was less to get wrong. But it really complicated the design of the processors. And the innovation that happened with RISC machines, really in the late 70s, was if you kept your instructions simple, you could execute an instruction in one clock cycle. That would simplify the hardware. That would lower the power consumption. And so we're just opening the door to mobile computers and mobile phones with that thought. Although it wasn't a really strong driving factor in the early days, you've got more transistors that you can use for registers and caches, so you're getting past those memory bottlenecks. And as programs were getting more complicated, you needed that extra memory for the program code. But you started pushing the burden onto the compilers for the languages to do the optimization, so that the programmers could live in a nice simple world of their programming languages, but things run very quickly. And arguably today, it's only the Intel x86 architecture that remains in the complex world. Everything else is simple. Excuse me. All the early machines ran one program at a time. In fact, just one user at the time. The key development that kind of changed that was the idea of multi-programming. That came from a machine called Leo 3, built by actually a catering company, Lions. Lions took EDSAC and turned it into a business machine for their own purposes, and they called it the Lions Electronic Office, Leo 1, and discovered they could also sell them to other people. And so for a while, Lions had a computer company. It ended up combined with all the other British companies in ICL, but they first had the idea of running multiple programs at once on a single processor, so pseudo parallel execution, and they gave us concepts of users, jobs, scheduling, and so forth. The key advantage of that structure was it overlapped I/O and computation, so you weren't wasting processor cycles waiting for devices. The I/O devices basically interrupted the process, and I've got data, and the data came in. And that was the birth of operating systems, and also the birth of the problem of you needed to protect the memory used by one program from the memory used by another, which is kind of the start of where the security problems crept in. And again, on top of multi-programming, you could start to do multiple users online to a machine. And that's the concept of multi-access. Back to Cambridge, Manchester did the design of the Atlas machines that gave you a machine of the appropriate scale. Cambridge took the Atlas design, simplified some parts of it, but built a multi-access system to show ideas of time sharing and so forth. The key Manchester contribution in Atlas was virtual memory. The idea that you can let the programmer think there's a huge amount of memory in which their program and data can run, and the hardware can automatically swap backwards and forwards between what is out on a disk or a drum and what's in the physical memory to give you that illusion of the large memory for the programmer, the small memory in which the actual computer is operating. That works, again, because program execution tends to be localized. You have this concept of a working set, and that the hardware can do the mapping for you. Again, it's kind of like a caching strategy, and it builds on the ideas of caches. And you can start to do access control by labeling who can read and write which page. So that came from Manchester. I'm going to skip a whole batch of other architectural ideas, but from running programs in parallel, then start thinking about, can you put processors next to each other so you can compute with arrays and vectors? Can you start building yourself multi-processors so that several computers can share a memory and get more performance that way? That started with mainframes and mini-computers. The IBM 360-65, I think, was the first symmetric multiprocessor. Gives you scalability of performance, but you start running out of bandwidth into the memory. The biggest machine you'll see in the museum is our 2966. That's microprogrammed, it has cache memories, it has pipeline, it's multi-programmed, it has virtual memory, it does multi-access and time sharing, and you can buy it, or you could, in 1985, in a symmetric multiprocessor version. And I will stop there. Thank you. Oh, there we go.
Thank you, Andrew. That was really fascinating to see very quickly that evolution of performance and the various processor architectures and programming. So now we're going to go to Professor Genevieve Lively, who's going to come via video.
She's sent a recording. So,
Sorry, she sent a recording. Okay. Genevieve is a professor of classics, Risks Fellow and Turing Fellow at the University of Bristol. She's a narratologist whose research interests focus upon narratives and narrative theories, both ancient and modern, and their impact on futures thinking. She has particular research interests in the stories that program cultural and socio-technical narratives about human interactions with new technology. She's currently seconded to GCHQ, working on a project examining anticipation and cyber risk with a socio-technical research team at the National Centre for Cybersecurity. She's also leading the Futures program at Describe Hub, which brings together technologists with social and economic sciences to support the adoption of new technologies. So let's hear from Genevieve on looking back to look forward.
First, thanks for inviting me to talk about looking back to look forward today. And sorry I can't be with you in person. I am Genevieve Lively, Professor of Classics and Turing Fellow at the University of Bristol. And I'm a narratologist with particular interest in the story frames, the schemata, and the scripts that program cultural myths and socio-technical narratives more broadly about human interactions with technologies, and there I include technologies both ancient and modern, and I should add, emerging. I'm the Anticipation and Futures Literacy Fellow for the Research Institute for Socio-Technical Cybersecurity, or RISCs, and I'm currently leading the Futures programme of the DSBD Describe Hub. Now, as I'm sure we're all aware, the prospect of DSBD presents a unique set of challenges. Because the full potential of DSBD, including issues such as use cases, socio-technical impacts, to say nothing of the regulatory frameworks that are likely to accompany its adoption, these are all situated in volatile, uncertain, and unknown future. So within the Futures programme that we've been running as part of the Describe Hub, we've been trying to help stakeholders across the DSBD ecosystem to better understand the specialist kinds of futures thinking that are required to take on and tackle these challenges. This means supporting stakeholders to avoid placing undue emphasis on the predictability, the certainty, or the clarity of the future of DSBD. And it requires the interrogation of a whole range of different types of desired futures. And were I in the room, you would see me doing bunny ears around that notion of desired futures. It involves resisting the assumption that present and historic trends are inevitable or will continue. And we call this chronocentrism or presentism. This includes taking steps to avoid simplifying or restricting the range of possible futures by focusing only on those that we deem plausible or probable or preferable. It really is about expanding the range of our anticipated futures to think about everything that might be possible. Now, crucially, this means looking beyond the future as a continuation of the past or the present. It means avoiding presentism, avoiding business as usual thinking. For example, when we imagine any kind of future, we necessarily imagine it from our present situation. So future projections, imaginations by business, by governments, are typically extensions of the present. They tend to be linked to known trends. But through a failure of imagination, in this regard, there's a risk that we end up populating the future with our present priorities, with our present concerns. I've given you some extracts from the current research on this thinking, and I'm particularly fond of that line from Bode, which reminds us that being able to think about the future is perpetually spoilt by our present incapacity to be sufficiently imaginative, to think the unexpected, to factor in surprise. And those are some of the elements of futures thinking that we've been trying to bring together through the Futures programme of the Describe Hub. We've been investigate the extent to which communities, organisations and individuals make sense of the new and the unfamiliar by assessing its resemblance to the old and the familiar. So testing its relation to so-called knowledge frames or knowledge scripts, and then making predictions of future patterns based upon templates that are unwittingly or otherwise shaped by prior knowledge and experiences. Now, the history of technology offers plenty of salient illustrations of that business as usual approach, but also the blind spots that are produced by such presentism. I've given you a few examples here, but I'm sure you can think of others from your own experience and from other comparative innovations in technological history. Thomas Watson, back in 1943, suggesting that there's a world market for maybe 5 computers. Thomas Watson. Ken Olsen suggesting that there's no reason why anyone would want to have a computer in their home. And this is great from Rutherford B. Hayes, talking to Graham Bell, but not on the telephone, about the telephone back in 1876, describing it as an amazing invention, but pondering who on earth would ever want to use one of them. Now, to help avoid the pitfalls of this kind of presentism or chronocentrism, the Futures programme has been helping to expose and try to better understand the heuristics and the knowledge shields that inevitably shape the imagination and the anticipation of the future worlds that DSBD has the potential to realise. And this is especially important if the wider DSBD programme is to imagine and then to deliver a future which isn't just a continuation reflecting the priorities and concerns of the now, if it's not to operate in a futures mode of business as usual. Now, creative, artistic and imagination-led processes have been identified by UNESCO, particularly under the rubric of its Futures Literacy programme, but have been identified by various bodies as particularly useful as part of the Futurist toolkit to help surface these different blind spots, biases and heuristics, useful as a way to challenge and break through those knowledge shields. That is, these creative, artistic and imaginative processes help us to enable a futuring process in which DSBD's future isn't tied to the status quo. It's not tied to the past or to the present of digital security and its technologies. Now, this is where the concept of looking back to look forward comes into play. Because when we look back at historic anticipations and imaginations of the future, and here I'm thinking particularly about the future of emerging technologies, we begin to surface and scope for some of those particular biases and limitations in our own imaginaries for DSBD and for DSBD Cherry. Let me show you what I mean. A series of images and imaginings of the future by various artists and illustrators were issued in France in the late 19th and 20th centuries. The first series was actually produced for the 1900 World Exhibition that was held in Paris that year. Isaac Asimov famously collected a set of these, which he published in 1986 in his book Future Days. The cards picture life in the year 2000 on l'an 2001, and they are notorious and I think rather glorious in their comprehensive chronocentrism. The year 2000 in all of these images is very much a projection of the past and a continuation of the present. New technologies and new modes of security are imagined here. But what really leaps out from these images is the failure of imagination. the reluctance or the inability to think beyond the technologies and the socio-technical systems of the late 19th century. So this is the late 19th century imposing its own template upon the year 2000. Across various of these illustrations, we find robots powered by steam, as we've just seen, flying taxis, not to mention flying policemen and flying postmen, are all powered by propeller engines, the cutting-edge technology of the time. Current technologies and systems predominate this very heavily technologically framed future, and current technologies provide not just the springboard for future imagination, but also the hardware and the kit for the imagination of future adaptations and sort of hybridizations, as we can see here. There are a number of scenes of domestic life like this, albeit a kind of sort of future life of the bourgeoisie in the year 2000. But existing technologies, so we can see the telephone, the gramophone, the telegraph machine, and the kind of cinematic projector, all combined here to predict the future glories of what I imagine as a sort of Zoom call on a grand scale. And here we can see in another image of domestic life in the year 2000, the imagination of somebody receiving an email or a text message handed on a phonograph roll by a servant. Now, these images of the future from the past didn't turn out to predict what life in the year 2000 would really look like. But they do have some important things to teach us about the art of futures thinking today. They prompt us to take seriously the attempt to picture the future of DSBD in the year 2030, say, or perhaps 2050, without falling into the same snares as those pictured on l'An de Milan. They prompt us to learn from this remarkable history of futures thinking to help enhance our own futures work in the present and in the context of the new and potentially radical innovation in digital security that's represented by DSBD. And now the future really is in the past, and I want to thank you for listening. And if you have any thoughts on imagining secure digital futures, past, present or future, please do get in touch. Thank you.
Well, that was a fascinating look into the world of presentism. That's a new word. Well, new word I've learned today, chronocentrism. So that's good. Thank you for that from Genevieve. And now we turn to Andrew Elliott, who is Deputy Director for Cyber Security Innovation and Skills at the Department for Digital Culture, Media and Sport, or DCMS. And he's going to talk about the ubiquity of computers in the digital world. Where's Andrew? Oh, sorry, there you are. Andrew, over to you.
Thank you. Well, gosh, it's been an exciting morning so far. I started off thinking about how I barely understood the past and trying to follow the detail of the architecture of computer systems really made me think how my brain has completely fried since my days as an undergraduate. I mean, I studied computer science 25 years ago and I still don't understand it. And now we've been told that we can't predict the future either. So looking both ways, I feel slightly confused. Anyway, can I just firstly start by thanking the team at Innovate UK for organising today. It's been a great exercise in trying to sort of learn about this technology that we are trying to develop here. We've heard a lot about the history of computing. And I'd just like to share a little parable with you, which demonstrates the tension in new technologies between security and innovation. When Marconi demonstrated his wireless broadcasting technology at the Royal Academy of Sciences in the early 20th century, Marconi became the victim of one of the world's first hacks. As a rival inventor, unimpressed by Marconi's supposedly secure system, hijacked the transmission and sent their own message to Marconi's Morse code printer. And for me, this demonstrates how the pursuit to get a new product quickly to market can take precedence over the need to make it secure. And secondly, how groundbreaking and advanced you might think your innovations are, there's probably someone else around the corner working out how to break it. So we've heard a lot about the past, but let's try and turn to the future, even though maybe we can't. We're all connected today in more ways than ever before. The internet is not just accessed via our computers. We're adopting connected devices at an increasing rate and into more aspects of our lives, in terms of our mobiles, fridges, and the cloud. But while this is positive, it's also made cybersecurity more and more challenging. Cybersecurity efforts are typically focused on mitigations and keeping up with patches. And this places the primary responsibility on the users rather than those building the systems. Although we've been taking steps to require products and services to be more secure through steps such as our product security bill currently before Parliament, in this world of increasing diversity of connected devices, we can't expect regulation and legislation to solve the problem by itself. So there's a need for technology providers to ask how they can provide cyber protection. How can their products be more secure by design? How can mistakes in development or configuration that lead to these vulnerabilities be prevented? Is security being adequately prioritized? So the DSBD program exists to help unblock the market failure that was stopping industry from introducing new technologies to block vulnerabilities. This vision is to radically update the foundation of insecure computing infrastructure to deliver secure by design technology. The DSBD capability provides new mechanisms to stop attackers by compartmentalizing data. And I feel like I now know why we've ended up in this position with data not compartmentalized. So it's been very helpful to understand the background to why we have this problem. And this is why we've partnered with Cambridge chip designer ARM in a 5-year research project to develop cyber attack resistant chip technology. This work has the potential to defeat hacks such as buffer overflow and side channel attacks. The first part of this task was to develop the Morello hardware, and that's the prototype board which the program has produced. Now we want to look at how this technology can be used to design new secure products and services. We want to help support and create a new ecosystem for people using and adopting this new technology and help them overcome any commercial or performance barriers to improving the security of their projects. The Digital Security by Design Technology Access Program, which is what today is all about, is your opportunity to get involved and experiment with this technology and to be part of that ecosystem. The way the program works is that there are 2 routes by which you can get involved. Get access to the boards and provide feedback to the ecosystem on the performance and security impacts of your real-world implementation of the Morello board. The first route is focused on startups, SMEs, and smaller companies that want to experiment with the technology. If you already have an idea of the use cases and the type of experiments you'd like to run, you'll have the opportunity to work closely with the program, receiving access to mentoring and technical sessions, Morello board access, as well as £15,000 grant funding to work on the technology. The second route is more light touch and more suitable for larger businesses not eligible for grant funding or startups and SMEs without well-defined use cases. you'll receive board access and be part of the early access adopter program. So the call for participation is currently open. The first cohort is open until the 6th of March. Further information is available on the website advertised earlier, dsbd.tech. There will be four cohorts over the next 2 years, so if you don't feel ready yet, please do register your interest on the website and find out how to get involved. Now, just at the end of last year, in December, I think, mid-December, the government published its new national cyber strategy, which set out how the UK will realise the opportunity of secure digital technologies. Digital security by design is one of the important opportunities in there to protect citizens and the wider economy from the harm caused by insecure technology products and services. The government is supporting UK SMEs to bring this game-changing technology to market, and cybersecurity firms are already a major contribution to the UK's tech success story. Last week, DCMS published its 2022 cyber sectoral analysis, available on gov.uk. And that shows that there are over 1,800 firms active in the UK cyber market producing cyber goods and services. And since last year's report, employment in the sector has increased by 13%, almost 53,000 employees. And annual revenues have now, for the first time, exceeded £10 billion. So the cybersecurity sector in the UK is growing fast and in good health, despite all of the challenges it faces, not least the lack of adequate skills and the difficulties finding a large enough workforce. I'm encouraged that our sector continues to evolve and innovate. We want to build on this success and take advantage of the UK being home of this new expertise and to build more secure products and services. Cybersecurity is not a standalone technology, but rather a cross-cutting enabler in a range of different contexts, being able to leverage this digital security by design technology to better secure the technology produced and used in the UK will not only underpin our national security, but can also be a source of commercial advantage. So I'd like to thank you all for your time and the interest you've shown in digital security by design. I'm looking forward to seeing how what I've said is converted into artwork later on. And I look forward to tracking your progress in creating secure technologies that take advantage and use this new technology in the future. Thank you.
So, thank you, Andrew, and thank you to all our speakers this morning. It's been great to look back on where we've come from and how now we need to look at how we need to focus our attention on the hardware in the same way as we've done with the focus on performance through the history of computing, as we've seen this morning. So that brings us to the end of the formal part of this morning. If you'd like to ask the speakers any questions, we have networking, so feel free to ask them during networking. Thank you for all for attending, both physically and online. And we look forward to those who can, either physically or online, to see you in Glasgow on 3rd of March. Details are on the dsbd.tech website. Thank you once again, and happy networking.